Gas chromatography, or GC, is a separation technique for volatile compounds such as organic molecules with low boiling points, in which the mobile phase is a gas. Within the topic of gas chromatography, there is gas liquid and gas solid, where the stationary phase is a liquid on a solid support, or a solid respectively, and it is assumed that during the elution the components do not interact with the mobile phase at all. To run a gas chromatograph, the sample is injected through a self-sealing rubber septum into an inlet that's surrounded by an oven. Ovens are quite important in this technique, and are usually at least around the inlet, column and detector, so that components don't condense in these areas. The sample is vaporized by the oven around the inlet, making it possible for the sample to be carried through the column as its components in gaseous form by an inert carrier gas / mobile phase. As is the case with all chromatography, the components are slowed by different amounts depending on their interactions with the stationary phase, and as it leaves a column it can be detected and the results processed using a computer. The mobile phase for gas chromatography is an inert and unreactive carrier gas, like neon, helium or hydrogen. The gases used must be as pure as possible so that there is as close to no chance of interaction as possible with the components when they are just carried by the gas. Sometimes the choice of carrier gas is dictated by the detector, but when the choice is available, the main three can be chosen for specific reasons. Helium is very popular in America because of its efficiency and fast flow rate, but it can be very expensive because helium is not naturally present in copious amounts. Nitrogen is used even less because of its low optimum gas velocity, which leads to long analysis times, though nitrogen is the most efficient of the three names if the separation is run at a high enough temperature. Of the gases that can be used for this method, hydrogen is preferable when pressure drop in the column is a limiting factor, because it is around half as viscous as nitrogen and helium. But the use of this gas is limited by the perceived, or sometimes real, threat of an explosion, which has led to specialised sensors that turn off ovens in the system if a leak is detected. The stationary phase is a metal column that is either packed in GSC or coated with a viscous liquid like an oil in GLC, which is most common. It is aligned so that the sample to be separated goes straight into the part of the column that is heated to above the boiling point of the sample, causing rapid volatilization. The temperature of the column must not exceed the boiling point of the sample, and generally the lower the temperature is, the more the components interact with the stationary phase. If the temperature is kept constant, the separation is referred to as an isothermal gas chromatography, but when the temperature is programmed during, then it is referred to as programmed time gas chromatography. The upper temperature limit for the elution is the highest it can be without causing column bleeding, as higher temperatures tend to reduce retention time or the decomposition of the components. To get the desired linear velocity of a compound through the column, the pressure drop should be regulated using valves. There are 5 main types of column used in GC, and they are standard packed columns with an internal diameter of more than 2 mm, containing particles with a diameter between 100 and 250 micrometers. Micropack columns that have a diameter of less than 1 mm. The ratio of the particle to column density should be smaller than 0.3. Packed capillary columns with a smaller packing density than standard and micropacked columns, with a diameter of less than 0.5 mm and a particle diameter to column density ratio of 0.2 or 0.3. The other 2 types are open tubular columns, which are becoming more popular and are only not more widely used because having them will mean new equipment, which would be more expensive, which has led to conversion kits being developed as a compromise. Supercoated open tubular columns have a liquid phase on their surface that is then covered with a layer of solid support material, making a vessel through the centre of the column. Wall-coated open tubular has a liquid coated onto a smooth or chemically etched column wall of a narrow bored column with similar dimensions to a capillary. The coating of the columns is important because it is the interactions between the stationary phase and the component which dictate how long the component is in the column. The main interactions are dispersion forces, which are an electric field that is caused by dipoles that change quite quickly. Induction interactions, which are between polarizable and permanent dipoles. Orientation interactions between molecules with permanent dipole moments that cause attraction to each other. And donor-acceptor interactions, which come from partial transfer of electrons from a filled orbital to an empty one. When the coating is a non-polar liquid, like a hydrocarbon, then dispersion forces become basically the only interaction, and elution then happens in order of increasing boiling point. When components have similar boiling points, the other interactions may come into account, but often there are other ways of separating components with similar boiling points, as will be discussed later. Polymers are becoming popular as well, as they have the desired higher boiling points, but can form either ether and ester links, which gives the solid support of the column more rigidity. As you would expect, there are a lot of types of detector that can be used, but the most common by far is flame ionization detector. Its use stems from the fact that when you can burn something in small amounts of ions are produced in the flame, and these ions can be detected with a little bit of modification. The detector itself is like a diagram in the learning pack, with the positive ions going into the flame and being attracted to the cathode, where they pick up electrons and become neutral species. Negative ions are attracted to the anode, where it loses electrons into the flame and become neutral species too. The gain and loss of electrons across the cathode and the anode causes a small electric current that can be amplified using more compound. This current can be detected. Often, GC is linked with mass spectrometry. Unfortunately, using this detector makes mass spectrometry not possible, because the flame ionizing detector destroys the sample, which would leave nothing to run a mass spectrum on. This detector is also limited in the fact that it does not respond to molecules like O2, HS, N2, CO2, CO, and SO2. When a molecule is in the process of being analysed, 3 different things happen to it whilst in the column. The component could condense on the stationary phase, stay in the gas phase, or dissolve in the liquid coating of the stationary phase. Components with boiling points higher than the column temperature will tend to condense at the start of the column, but will usually re-evaporate and condense again further along, and then re-evaporate again until it leaves a column. Components that are more stable in the liquid coating of the stationary phase will spend more of its time in the liquid and not long moving in the gas and mobile phase, which means it takes longer for the component to leave the column and will have a higher retention time. This means that GC can be partition chromatography, like TLC, as its components can split their time between 2 phases. Gas chromatograms show the components as portions of the sample, with each peak corresponding to a particular substance, with a particular retention time, which are measured from 0 to the centre of the peak. The portion of the component can be worked out using the area under the peak, as this is proportional to the amount of original sample. But it is important to point out that the area is what matters and that the tallest point is not necessarily the most abundant component. This process is used extensively for many industrial processes, but it is particularly useful when it can be adapted for separate components with similar boiling points. For example, benzene and cyclohexane have boiling points of 80.1 degrees and 81.4 degrees respectively. When the situation is similar to this, the separations have to be made on a basis of their interactions with the stationary phase, and as they are both non-polar molecules, the coating will have to be very specific. The main difference between the components is that benzene has a pi electron cloud, and so is more acceptable to induction effects. This means that a polar solvent would have some interaction with the benzene and very little with the cyclohexane, and then, by using the general rule of like dissolve like, then an aromatic solvent would be used to create an interaction with benzene. A good solvent for this would be dianyl phthalate, and using this created a relative retention time of 1.6, which is a very good separation. For use in inorganic chemistry, volatile derivatives of compounds need to be made, and detectors have to be added so that elemental analysis and special detectors can be used after the gas chromatogram. Modern development of this technique has meant that analysis can take place at temperatures high as 400 degrees C, and for molecular weights of less than 1,000, and in some special cases higher temperatures and smaller weights have been run too. This technique is limited by the fact that in most cases the components have to be volatile and thermally inert or stable at the temperature needed for volatilization. GC is not ideal for big samples, and this is mainly because the theory isn't always reliable when choosing a stationary phase, and trial and error is still very much needed. A component can sometimes hide under more abundant or similar compound and show as one peak, as well as potential that thousands of chemicals could have the same retention time, peak shape, and or detector response. That being said, this method is inexpensive, efficient, fast, widely available, and relatively straightforward, but perhaps the best feature of GC is that only a small amount is needed to analyse a sample, and as long as a flame ionizing detector is not used, the method is non-destructive, which is particularly attractive when a compound is expensive to make.